One thing we can make note of with the first derivative test and optimizing for the absolute extreme values goes along something like this. It says suppose that c is a critical number of a continuous function f defined on an interval. If f prime of x is greater than 0 for all x less than c, and f prime of x is less than 0 for all x greater than c, then f of c is an absolute maximum value for f. Similarly, if f prime of x is less than 0 for all x less than c, and f prime of x is greater than 0 for all x greater than c, then f of c is an absolute minimum value of f. So it's working out something like this, where on the less than side it's increasing and then it starts decreasing. And so that's why we can assume if that's happening for everything on the less than side and the greater than side of c, we'd have an absolute maximum value at c. And similarly, on the other hand, if it goes down, it's decreasing and then increasing after c, then we know there's an absolute minimum value at that location. We're going to use this in applications like the next one here that says find the point of the parabola y squared equals 2x that is closest to the point 1, 4. So let's take a look at what we're dealing with here. Y squared equals 2x is actually a sideways facing parabola. We're trying to find the distance to this point 1, 4. What's the shortest distance away from the parabola to that point? So what we're going to do here is minimize the distance. The distance formula being given by d equals the square root of y2 minus y1 all squared plus x2 minus x1 all squared. In particular, we'd like to find the distance from an xy point on the parabola somewhere, the one that's the closest, to the point 1, 4. So under those conditions, we'll write our distance formula as d equals the square root of y minus 4 all squared plus x minus 1 all squared, where I'm using this as my x2, y2 in the formula, and this one is my x1, y1 in the formula. From our formula, y squared equals 2x, it follows that x is equal to 1/2 y squared. And as a result, I'm going to substitute that in to the distance formula. We'll have d is equal to the square root of y minus 4 all squared plus 1/2 y squared minus 1 all squared. I'm going to square both sides so that I can reduce down that square root, make it a little bit easier to handle. So d squared is equal to y minus 4 all squared plus 1/2 y squared minus 1 all squared. So in order to minimize here, I'm going to minimize the distance squared. So let's call that a function called f of y equal to d squared. And if we minimize the squared distance, we're minimizing the non-squared distance as well at the same time. So first off, we're going to need to find the first derivative, f prime of y. We take the derivative of the d squared equation up above. It's going to look like 2 y minus 4 to the first power, that's the chain rule, times 1, plus 2 times 1/2 y squared minus 1 to the first power, times 1y. And I'm going to work on cleaning this up a little bit. We're going to distribute this 2 into the parentheses. I'm going to distribute this 2 also in the parentheses. We can also distribute the y into the parentheses as well. So f prime of y would equal to 2y minus 8 plus y cubed minus 2y. We're going to need to set this equal to 0 to find the critical values. So 0 equals, once I combine together the terms, y cubed minus 8, because we're going to see those two y's go way up there. So y cubed equal to 8, and from there it follows that if we take the cube root, y is equal to 2. And that's our critical value. And so if I visualize what's going on here with the number 2, and if I choose some test values on either side and check those with the derivative, f prime of 1 would equal to 1 cubed minus 8, which is equal to negative 7. So it's a negative number, it's decreasing. And then if f prime of 3 would be equal to 3 cubed minus 8, which is positive 19. Being that it's positive, it would be increasing. So this shows that we can be assured that at 2 there would be a local minimum. So the closest point has a coordinate of y equal to 2, and the x value would be equal to 1/2 times 2 squared, or just 2. So the coordinate 2, 2 on the parabola would be closest to the other point 1, 4. Now in this example here it says a man launches his boat from point A on the bank of a straight river 3 kilometers wide and wants to reach a point B 8 kilometers downstream on the opposite bank as quickly as possible. He could row his boat directly across the river to point C and then run to B, or he could row directly to B, or he could row to some point D between the points C and B and then run to B. If he can row at 6 kilometers an hour and run at 8 kilometers an hour, where should he land to reach B as soon as possible? We assume that the speed of the water is negligible compared to the speed at which he can row. So this picture kind of shows how this is set up here. We're starting from this point A, and we have a couple options here, or I should say 3 options in a way. We could just go straight across to point C, or we could just go straight downstream at an angle down to point B, or we could go to a point in between and see if we can't get to there and then go the rest of the way on land to point B. So it's already kind of set up with the variables we need to use here. What we're going to do here is let x be the distance from some point that we could possibly go C to the other D point downstream. So we can set up here, we're going to notice how we have sort of a right triangle situation going on. We'll kind of focus in on that triangle ACD. And if this side is x and the width of the river is 3, then using Pythagorean, it tells us that the distance from A to D would be the square root of 9 plus x squared. We can also tell the distance from D to B would be the total of 8 minus whatever x could be. So our goal here will be to minimize the possible time it could take, depending on where the point is rowed to along the coast. And what we'll do is we'll consider, of course, that the rate, the speed, is distance over time. And so if I rewrite this in a different way, time would be equal to distance over rate. So here's how we're going to set things up. The total time it takes is the sum of the time it takes to travel on water plus the time it takes to travel on land. And so using the notation and everything we have up above, we're going to call this a function called t of x for total time. And we're going to rewrite this as the square root of 9 plus x squared. That's the total time it takes to travel on water over the speed or the rate, which it told us is 6 kilometers an hour, plus the time it takes to travel on land, which would be 8 minus x, divided by the rate of 8 kilometers an hour. We can make note that the variable x can go from 0, which is if they go straight across the river, row downstream, and don't travel on land at all the way to 8. 8 would be if they went straight across and then all the way down along the land. So in other words, 0 less than or equal to x less than or equal to 8 are the lower and upper bounds for the variable x. Since we're trying to minimize total time, we're going to have to take the derivative of t. So let me rewrite t as a slightly different function here. Let's write it as 1/6 times 9 plus x squared raised to the 1/2 power plus 8 over 8 minus x over 8. Or in other words, let's rewrite that as 1/6 9 plus x squared raised to the 1/2 power plus 1 minus 1/8 x. So I'm going to take the derivative here, t prime of x. That's going to be equal to 1 over 12, 9 plus x squared raised to the negative 1/2 power times 2x, that's the chain rule, minus 1/8. We'll reduce down the 2 and the 12 here in the fraction, so we can rewrite this as t prime of x is equal to x over 6, 9 plus x squared to the 1/2 power minus 1/8. Now what I'd like to do is find the critical numbers so that we can optimize this thing. So let's set it to equal to 0. And we're going to solve. We can go ahead and add over the 1/8 to both sides. And then what I'll do here is I'll cross multiply. And we'll receive here from that is 6. And I'm going to rewrite that as square root of 9 plus x squared equals 8x. I'll go ahead and divide out the 6 from both sides and rewrite this as square root of 9 plus x squared is equal to 4x over 3, or just 4/3 x. Then I'm going to square both sides, and that'll change this into 9 plus x squared equals 16 over 9 x squared. Let's go ahead and clean up that fraction there. Let's multiply both sides by 9. So it would look like 81 plus 9x squared equals 16x squared. As a result, we can say that 7x squared is equal to 81, or just x squared is equal to 81 over 7. And so we can take the square root. Technically, in general, it'd be plus or minus. But in this case, since we're only dealing with measurements of distance, only the positive value would make sense. So it follows that x is equal to the positive square root of 81 over 7, which is going to be approximately 3.4 when rounded off to the nearest tenth. So if we check the value of total time at 3 different values, the lower limit, the lower bound for x was 0, the 3.4 critical value we just determined, and 8. And so for 0, if we plug that into the total time function, it would look like square root 0 squared plus 9 over 6 plus 8 minus 0 over 8. And that comes out to be 1.5. That'll be the measurement of hours to travel from point A to point B. If I plug in that same thing, but for 3.4, I came out with approximately 1.3 hours. And for 8, I plugged that in, I got approximately 1.42 hours. So now we can see the quickest way to go is to go downstream a little ways, and then from there go on land the rest of the way. So we can say that it's the quickest to go 3.4 kilometers downstream and then travel from there onward.